Okay, hi, good afternoon, I guess. Now it's afternoon even here. Thank you for coming back. Again, if people don't mind turning on their video, that would just help me to get some feedback from faces. Thank you. And let's continue from where we stopped last time. Just bring the screen a little bit closer. So the last thing that I did yesterday was write down. So we talked about proving the strong perfect graph theorem, and we said we're going to try to prove a triple of theorems. Theorem 1 that says every Beige graph is either basic or admits decomposition. Theorem 2 that says every basic graph is perfect. And then theorem 3 says we can use the decompositions. We can show that the decompositions cannot occur in the minimal counterexample. And I called it the winning triple. And then the very last thing I did was tell you what was theorem 1 that we actually proved, because it's winning triple, you can kind of fill it in however you like. You can play theorem 1 of theorems 2 and 3. So what we ended up proving is that G be bearish, then one of the following holds. 1, G is basic, meaning bipartite, complement bipartite, line graph of bipartite, complement of line graph of bipartite, or double split, or 2G admits SQ partition, balanced Q partition, or 3G or G complement admits adjunction. Okay. And then, as we already said, you can prove that all basic graphs are perfect, and you can prove that the minimal counterexample does not admit a balanced Q partition or adjunction. So I just want to spend maybe 20 minutes talking about the proof of this theorem, and then we'll move on to something else. So obviously, I'm not going to show you the whole proof, but I just want to give you an idea for how you would go about proving something like that. The difficulty with proving a theorem with so many outcomes is that at any given moment, you don't know what you're trying to prove. Are you trying to make your graph to be bipartite and not have any triangles, or are you trying to get your graph to be complement bipartite and not have any stable sets of size 3? It's really helpful if you know what you're trying to prove, right? We all know that. So the trick is you try to find something in your graph that would force a certain behavior. So you keep proving, a bunch of lemmas that say, if G contains something, then G has a Q partition. If G contains something else, then G has a 2G. And the trick is to find this kind of forcers, to find things that would rule out as many outcomes as possible. So in this spirit, the very first theorem we proved of this type, which, and then it's not theorem 1 if you follow the proof, but it is theorem 1 in the chronology. The very first theorem we proved was the following: let G be bearish and assume G contains this. Right, so just this 8-vertex subgraph, induced subgraph, contains from Yolo's means induced. Then G means a balanced Q partition. All right, so this sounds a little bit like a miracle, but let's see why, if you believe theorem 1, that if you believe that what you're trying to prove is true, why this has to be the case. So if you look at this graph, it has a triangle, so it's not bipartite. It has a stable set of size 3, so it's not complement bipartite. It has this, which is called a claw. 1, 2, 3, 4. So it cannot be a line graph. It's not hard to convince yourself that line graphs don't contain claws. it contains the complement of a claw. So the complement of a claw is this graph, and it contains that because go 1, 2, 3, 4. And you can, if you still remember what double split means, you can check that it's not a double split graph. So anything that contains that cannot be basic, right? Basic graphs are closed undertaking induced subgraphs. So if you contain that and this is not basic, then your big graph cannot be basic either. So that's very good. We cut down the number of cases from, the number of possible outcomes by 1, 2, 3, 4, 5. Right, by 5 options. So more or less, right? So all that's left is a graph that contains that might admit a skew partition and might admit two general complement. And then you just get lucky. It comes out to be always a skew partition. So, and the way it always comes out to be a skew partition, you can notice. So remember what a skew partition is. It's a partition of the vertex set into 4 parts. That look like this. B is complete to C and A is anti-complete to D. So notice that this already admits a skew partition, just this little 8 vertex graph. So you call this vertex B, you call those 4 C, you call this A, and you call those D. And you can design rules for how to extend this skew partition of the 8 vertex graph to the skew partition of the whole big Bash graph, right? Things like if a vertex has a neighbor in A and has a neighbor in D, then you must add it to B or C, and you can check that you can always set it to one of that. So you can just design rules for how to extend this skew partition. It turns out it always works. All right, so this was the very first theorem, and this is kind of the spirit, right? You found something that forces a certain behavior. So now let me show you the real first thing that we proved. Questions about this? So let me show you the real first thing that we proved. So again, as always, G Berge. Assume G contains a line graph of F, where F is a bipartite subdivision of a 3-connected graph H, which is not K4 and not K6. Right, so your graph G, your big Bash graph G, contains a bipartite subdivision, or contains the line graph of a bipartite subdivision F of some graph. Just for the sake of my presentation, let me not say this. Let's just say bipartite subdivision of a 3-connected graph. I need to tell you that it's a little more details here. So it needs to be a little bit non-trivial. You need to make sure that enough edges are subdivided. But at the level of detail which I'm going to show, you this proof, it won't matter. So it's a little bit more. And then G admits a balanced skew partition. A balanced skew partition, or G is a line graph of vector. And so you can check that if you contain the line graph of a vector graph, the line graph of a subdivision of a 3-connected graph, a lot of the outcomes, a lot of the basic outcomes are not possible. If your subdivision is a little bit non-trivial, then the only possible basic outcome is that your whole graph is a line graph of vector graph. And then, sorry about that. So G admits a balanced skew partition or a 2-join, or it's a line graph. And then there are two two possible decomposition outcomes, balanced Q partition or two. Okay, and let me show you a little bit of white string. So again, we're proving that if you contain, and the picture that I want you to have in mind is this picture. So let's just think for a minute what this picture is. So this is the line graph of a subdivision of K4. At K4 is this graph. And if you construct the line graph of K4, it's this picture with all this path contracted. But if I subdivide it a little bit, something like that. So I think with high probability, this is a line graph of that. Possibly I need to change the subdivisions. Okay, so this is a line graph of subdivision of K4. And so the theorem is that if you contain something like this, then your graph either grows to be a line graph or it admits a decomposition. So now let's think about for a minute why something like this might be true. So here's an important fact about perfect graphs, or about Besch graphs. So if you have a Besch graph, then you do not contain an induced subgraph looking like this. This is called a pyramid, or sometimes we say this vertex is linked to this triangle. So in a Besch graph, you cannot link a vertex to a triangle. Why? Because look at this picture. Two of these paths have the same have lengths of the same parity. Let's say this and that, but then this is a node hole. This is an induced odd cycle. Right? Well, so you should say, what if they're both edges? Then this induced odd cycle is a triangle. And I should say that's right. That's node hole the pyramid. So a pyramid means a picture like this, where at least two of the paths are subdivided. At least two of the paths have internal vertices. Right, so fact G dash implies G does not contain. Okay. All right. So, and again, let me just say it again. A pyramid means a triangle, and the vertex and three paths from the vertex to the triangle looking like this, where at most one of the paths has length 1. At least two of the paths have interior. All right. So now, what does this have to do with that picture? Well, imagine you have this graph, and now you have a new vertex, right? So this is part of your big Besch graph. You're trying to understand your big Besch graph that contains that. Now you have a new vertex with a lot of neighbors everywhere. Well, there's a lot of potential here for getting pyramids, right? Like, for example, in what I've drawn, you can go this way, and so I'm going to this triangle. I can go this way, and I can go that way, and I can go that way. And that's a crooked pyramid, right? Okay, so what does that tell me? Well, the fact that I found three paths from this vertex to that triangle doesn't mean that it's impossible. What it means is that one of the paths is very short, two of the paths are very short, right? And I could find a vertex with three paths to a triangle, except then two of the paths need to be edges. So in this picture, what that means is actually in this routing, two of the paths are very, very short. So this vertex has two neighbors in this triangle. It has to be like that. All right. So, okay, what is the theorem I attempted to show you the ideal proof of? If you have a vertex with a lot of, so you start with a line graph of a biplane subdivision of a three-connected graph, and if you look at the vertex, if it has a lot of neighbors, then it has at least two neighbors in every triangle of the line graph. right? So now the question is, what's a lot of neighbors? Well, a lot of neighbors means I can find this kind of routing for every triangle. And it turns out that the following is true. So again, in this picture, and I'm just doing this example, but you can say this all more precisely. Same picture as I had before, more or less. So there are two kinds of vertices. So this is my LF, and then let V being G minus LF. Then there are two possibilities. Actually, there are three possibilities. Maybe V is small, and small means either all its neighbors are in one path like that, or all its neighbors are just in one triangle. Neighbors, one path, or in one triangle. Or V is big, and big means at least two neighbors in every triangle. Next one. Or there's another option. And the other option is, and let me just draw it for you, it's a vertex that looks like this. So if you look at this vertex, let me erase all the rest from the picture. If you look at this vertex, you'll notice, you can't link it to any triangle, and there's no chance to use our fact about there being no pyramids in a perfect graph. And it's not small, it's not big. So what is this vertex? Well, the thing is, what this vertex does, it allows you to make a bigger line graph. Let me make it in a different color. So the graph I started with was the line graph of this, with some appropriate subdivisions. And what this vertex does, it adds an edge like that. And if you've worked with line graphs, you can see that I'm not lying. If you haven't worked with line graphs, you can look at it later and convince yourselves. But the black is the line graph of this, and with the red, it's the line graph of the graph with this edge here. Okay, well, so remember I said F is some line graph of a biped subdivision of a three-connected graph. Well, F is some biped subdivision of a three-connected graph. Make your F bigger. Start with the biggest F you could start. You could find, and then you're not going to find vertices like this, right? The vertex like this allows me to enlarge F. So if I choose F maximum, assume F is chosen maximum in some sense, then this doesn't happen. And then in fact, it's either one or two. Okay, so there's somehow dichotomy. There are vertices with a lot of neighbors and vertices with very few neighbors. And notice that if I look at one vertex with a lot of neighbors, that's a good place to look for a skew partition, right? Like if I look at one big vertex, it has at least those neighbors and maybe some more. Well, take this vertex and all its neighbors. Call this for, remember, skew partition means CD, AB. So call this vertex C, call, let's say, those guys D, and then call this part A, and call everything else in the world D. I changed my notation, so let everything else in the world be, then that's a skew partition. So big vertices are good for finding skew partitions. And it turns out, and maybe let me not show it to you, but the analysis we just did for one vertex, you can do it for sets of vertices. So you start with this big line graph. You partition the world into small and big. And then it turns out that components of small are still small. Components of small only attach locally. I'm cheating a little bit. One thing that could happen with the component of small is that it would attach like this. So this is not small. This is like a component of small vertices, but the union of the attachments in the line graph is not just in one path or in one triangle. Well, but then, you know, this red path looks just like the black path. So maybe you could, you know, so why did you start with the black copy of the line graph instead of with the red copy of the line graph? Well, don't choose, take them all. So instead of having one line graph, you can take, you should take kind of all alternative paths. And then after you've done that, and I realize this is not enough detail to explain it, but to actually understand it, but it's some rule about generalizing this structure to include all alternative paths. Right, so instead of having this, now each of those guys will turn into a set. And then between them, there will be some set of paths. And now after you've done that, it turns out, so you still have, you need to prove it, but it's true, you still have this classification into big and small vertices. And now suddenly the world is in order. Because if you look at the component of small vertices, it has small attachments. Either it only attaches at one path, or it only attaches at one generalized triangle. If you have a component of big, so with big vertices, the trick is you need to understand that you should look at components, you should look at anti-components. And anti-components means a maximal set that's connected in the complement. That is, you know, it's perfect graph, so everything you say, you also want to say it in the complement. So we have connected, and then we have anti-connected. Anti-connected means connected in the complement. And you have component, and you have anti-component. An anti-component means a component of the complement graph. So anti always means going to the complement. So for big vertices, the trick is to look at anti-components. And so let me just write down some of what I said. So generalize the structure. To include alternative paths. We call it generalized line graphs. Generalized line graph. And I want you to remember this word because I hope to come back to it when I talk about porphyry graphs. And then we can prove that components of small vertices have local attachments, meaning a component of small vertices only attaches at one, what we call strip, so one kind of collection of paths, or at one node, one generalized triangle. And then if you look at anti-components of big vertices.
Sorry, can you just move the screen?
Sorry about that. Anti-components of big vertices have big common neighbors. So what does that mean? So a big vertex had two neighbors in every triangle. Now, if I look at an anti-component of big vertices, this is anti-component of big, it will be complete to all but one set in each triangle. I'm not going to draw the last ones. So just like I convinced you that if you just have a line graph and one big vertex, taking this big vertex and its neighbors gives you a skew partition, now you can do the same thing with this anti-component of big vertices. Take this anti-component, take its common neighbors. That's a good thing to do for the center of a skew partition. And that will break the line graph with the small attachments, giving you a skew partition. And if there are no big vertices, you can convince yourself that there's a true. So I think maybe I may not talk about this anymore, but the key, so there are two key insights here. You start with this big line graph, and the first thing that happens is that vertices break into two categories, small and big. Right? There are no kind of vertices which are intermediate. And then after you've generalized the structure a little bit more, it turns out that small vertices, even their connected subsets, still attach locally. And big vertices, even their anti-connected subsets, still have a lot of common neighbors. And that's exactly what a skew partition is, right? What's a skew partition? It's when you can partition a graph like this, right? So you want some people with so many common neighbors that they separate something from something. So having some people with a lot of common neighbors and some people that attach locally is, is your winning ticket. Right? You put big vertices here with their common neighbors, that's good. And then the rest of the line graph breaks like that. All right, so I think that's enough on that. Are there any questions? See, I see something in the chat. Okay. That's very good. Self-answering questions. Somebody else answered. Perfect. All right, so let me erase this. And the next thing I want to talk about is recognition algorithms for perfect graphs. Recognizing perfect graphs. So first of all, I should say that this is after the proof of the strong perfect graph theorem. So recognizing perfect graphs and recognizing Beige graphs is the same question. And as probably most of your intuitions tell you, it's much easier, if you're going to try to solve this problem, what you should do is look for the structure. You should check if there are odd holes or odd antiholes. You shouldn't check, is the clique number the same as the chromatic number in every induced subgraph? Right? Doing anything with chromatic numbers is hard. But testing for an induced subgraph, testing for a structure, there is some hope. So the next thing I want to say is that this problem was first solved in 2006 by me, Borjos, you, Seymour, and Pushkovich. And what we proved is that can test if an input graph is Beige in time n to the 9, right? And n is the number of vertices. I'm ignoring constants, but that's it. But right, so just to remind you, what's Beige? Beige means no induced odd cycles and no complements of induced odd cycles. So a much more natural thing to do here is to is to test whether your graph contains a node hole, to test whether your graph, and to test whether your graph contains the complement of the node hole. It's called the node antihole. But we couldn't do that. The way our algorithm worked, it stopped and it said, this graph either has a node hole or it has a node antihole, but we don't know which one it is. And the reason for that was that we weren't checking directly for odd holes or antiholes, we were checking for certain behavior that we knew bearish graphs exhibit. And the algorithm was running and it would find that this behavior doesn't occur, and then we knew that the input wasn't bearish. But the question of testing for odd holes remained open. So then in 2020, with Alex Scott, Paul Seymour, and Sophie Spurkel, we were able to get this much more natural, to solve a much more natural problem, testing for odd holes. And test input graph contains an odd hole. And same rank. And the thing is, right, so first of all, of course, you can use this to do that, just run this algorithm on G and on the complement of G. And secondly, this is easier. Somehow, we knew where, like this one only wasn't testing for odd holes. This one only needed to stop when the graph is not bearish, but we didn't know which way it was not bearish in a couple of places. And what this did was basically do something smarter in those couple of places. All right, so I'm going to tell you something about that. I think what we'll do today is, so these algorithms have 3 parts, and I think probably what we'll do today is do parts 1 and 3 that are the same in both, and then tomorrow I'll show you the new middle part of that. All right. Oh, and another thing I should say is that there's another group, but unfortunately I can't tell you their names, I'm sorry about that, who were recently able to make this a little bit quicker. I think they can now do n to the maybe 8.5 or something like that, and same here. I think same here. But I'm not going to tell you about the algorithm because I don't know. But it's kind of, it's similar ideas, just there's some things that you do more cleverly. Okay. So let's. So let's say we're doing testing for results. And again, just to remind you, an odd hole means an induced cycle of odd length, but not length 3. C5 is an odd hole, a triangle is not an odd. So the first step is something that we call test for easily detectable configurations. So what does that mean? That means testing for things that's easy to test for. For example, you can test for C5. It's easy to test for C5. Go through all 5 tuple vertices and check whether this is whether they make an induced C5. Here's another one, which is a little bit harder, but not very hard. We draw it, and then I'll tell you what this drawing means. So remember, I already told you dotted edges means non-edges, solid edges means edges, wiggly edges means I don't care. Okay, so what's this then? It's vertices called 1, 2, 3, 4, 5. 1, 2, 3 make a 3H path. 1, 2, so 5 is adjacent to 1 and 4. I don't care what kind of edges there are between 5 and 2 and 3. But this is called P, is a path from 1 to 4 with no neighbor of 2, 3, or 5. And so again, a 3H path. So another way to say it, it's a path and then a 2H completion to a hole for it and a 3H completion to a hole for it. This is probably true. So there are two nice things about joules. One is that you can easily test for joules, and two is that joules cannot occur in Besh graphs. So first, let's say why joules cannot occur in Besh graphs. Well, suppose you had a Besh graph and you contain a configuration like that, then how long is this path? Well, I can complete it to a hole like this, so it's even, but I can also complete it to a hole like that, so it's a contradiction. Okay? Besh graphs do not contain joules. Okay, so now why can you test for a joule? Well, that's because go through all 5 tuples of vertices that look like this. Change color. Right, so go through all 5 tuples of vertices so that 1, 2, 3, 4 make a 3H pass, and 5 is adjacent to both its ends, and I don't care what's here, and I don't care what's here. And now delete the neighbors of 2, 3, and 5. Except don't delete 1, 4. It's not a great place to write. Sorry. G prime is G minus the neighbors of 2, 3, and 5, but don't delete 1, 4. And now ask, can I get from 1 to 4 in G prime? Which is something you can do. It's Dijkstra's algorithm. Yes. If there is a path from 1 to 4 in G prime. Right? And if there is such a path, then this is a joule, and if there isn't such a path, then this 5 tuple doesn't give you a joule, so move on to the next 5 tuple. And if you know 5 tuple is a joule, then there's no joule. Right, so you can do it probably at the time n to the 7, n to the 7th if you're not in a hurry, and n to the 8th. Okay, so you can test for joules, and the thing is that if you find the C5, you stop and you say there's an old hole. If you find the joule, you stop and you say there's an old hole. So now let me show you the last easily detectable configuration that is not quite as easily detectable. But on the plus side, we've already met it, and it's a pyramid. So I'll draw it here. So it's a triangle and a vertex. A, B1, B2, B3, B1, B2, B3, and the rule is at most one of B1, B2, B3 has length. All right. So as we already said, the Besh graph does not contain a pyramid, right? 2 of the paths would be the same length. I'm sorry, not the Besh graph. So we're now doing odd holes. A graph with no odd hole doesn't contain a pyramid because 2 of the paths would have lengths of the same parity, and that would be an odd hole. So now the question is, how do you test for pyramids? So there's nothing obvious you can do like with a joule, but it turns out you can. And yeah, let me show you how to do it. So Besh and if G contains a pyramid, then G contains an odd. So, but now I'm sure, and these are all the easily detectable configurations. C5, in fact, you don't really need to test for C5, but it's just too tempting, the jewel and the pyramid. Okay. So let me show you how to test for that. Dmitry, can I ask you a question? What's better, fading black or blue?
Black.
Or, black?
Black.
Okay. How bad is it? I can like walk across the room and get another black. Is that worth doing?
Yeah.
Okay. Excuse me, I'll be right back. It's not a big room. I'm back. All right, so testing for pyramids. Okay, so, and the reason I want to show it to you is because it's a nice method. It's something we call the shortest path detector. And there are all kinds of things you can test for using the shortest path detector. So let's say I want to, let's kind of think about it for a minute. I want to test for an induced subgraph. So, I can test, like it's easy to test for an induced subgraph on 10 vertices. It goes through all 10 tuples. The problem is when the graph you're testing for has unbounded size, right? Well, the family of graphs you're testing for contains graphs of unbounded size. But it would be nice if you could say, I can run through all 100 tuples of important vertices. And the rest I can fill in however. And this is kind of the idea here. So it turns out that you can prove the following. Let P be a pyramid. Actually, sorry, let me do the definition first. So if you take a pyramid, and let me define something called its frame. So what's its frame? It's A, B1, B2, B3. And then the midpoints of the path. And then the three neighbors of A. Let's call them 1, S2, S3. So MI is the midpoint of B. And what do you do if PI has one edge, or what do you do if PI has odd lengths? And you can define this more precisely. But roughly, it means MI is the midpoint of P. And let's say this pyramid is called P. So then A, B1, B2, B3, M1, M2, M3, S1, S2, S3. This tentacle is the frame of P. Okay? And now what I'm going to prove is that all that matters is a frame. If you pick the right frame, it doesn't matter how you fill in the rest of the path, you're going to get a pyramid. Right? Which is kind of what we were saying. Like, it's a problem when every vertex matters. If only 10 vertices matter, then we're okay. So what do I really mean? Now I can tell you the term. So let P be a pyramid in G with the smallest number of vertices.
Dr. Chernovsky, is the frame supposed to be a set of vertices or like a subgraph of P?
It's a tentacle of vertices. It's an ordered tentacle.
Thank you.
And let F be a frame for P. And now what I'm going to do is fill it in with shortest path. So let Ti be a shortest path in say from Bi to I can still see my pyramid, yes. And I'm going to put a blank here, but what I mean is like this path could plausibly be in the pyramid. If it's T1, so it's a path here. So I don't want it to have neighbors to B2 or to A or to M2, right? From the point of view of the frame, this path does what it's supposed to do. So maybe I'll write with no chords to the frame. Right? So from the point of view of the frame, this path could be a path of the pyramid. And then let Ri be a shortest path from, so what did we do? So far we had Bi to Mi, now let's have Si to Mi. Si to Mi. And again, with no chords to the frame in the same sense. Then, if you take the union of all of this, you get a pyramid. F union T1, T2, T3, union S1, S2, S3 is a pyramid. Pyramid P prime with B of P prime with the same number of vertices. So let's understand what this theorem says. So it says if you start with the shortest pyramid and you take its frame, so that's some tentacle of vertices, and now you try to fill in, right? So a frame is some part of the pyramid, but there are 6 paths missing. Let me maybe just so that I could talk about it a little bit more clearly. Let me draw a picture here. So the frame is this tentacle here. And after I've fixed the frame, what's missing? 6 paths are missing. A path between these 2 vertices, a path between these 2 vertices, and so on and so forth. What the theory tells you is that when you look at this frame, it doesn't matter how you choose the 6 paths. You're still going to get a pyramid. You need to be a little bit careful, like when you take a path between these 2, don't use neighbors with that vertex. But that seems fair. Now, the good news is, if you believe this theorem, then you can test for pyramids, right? What do? You run through all possible tentacles, and you pretend it's a frame for the shortest pyramid in the graph. What does it mean, you pretend it's a frame for the shortest pyramid in the graph? It means you try to fill it in with 6 shortest paths like that. If you ever succeed, right? If you ever look at the union of the frame plus the 6 shortest paths, and it's a pyramid, well, you know you found a pyramid. You stop and you say this graph has not hole, this graph has a pyramid. Actually, we're testing for pyramid. You stop and you say this graph has a pyramid. But the amazing thing is that if you never found a pyramid in this process, that means your graph doesn't have a pyramid. Right? And let me say this again. Why? Because suppose G has a pyramid, then it has the shortest pyramid. When I look at the frame for the shortest pyramid, this theorem tells me I'll find it. My 6 shortest paths, their union will be pyramid. Okay? So it's nice. It reduces the problem from testing for something unbounded to running through all tentacles of vertices and doing some calculations. Let me write something down about it. Unless other questions, actually.
Can I ask a real quick question?
Sure.
Do we need an additional restriction that like T1 and S1 don't share any vertices other than M1, or is that taken care of by the chords? condition?
So you don't need that. You can choose the T's and the S's independently. It's a
I see.
theorem that they'll come out right.
Oh, wow. Okay, cool. Thank you.
Sure. Anything else? There are other more sophisticated algorithms where you do it the way you suggested. You choose the first pass arbitrarily, and the second pass you say, well, now I demand that there are no cores to the first pass. But here it's just comes out in a simple way.
I see. Thank you.
So algorithm to test for pyramids. So run through all tentacles A, B1, B2, B3, M1, M2, M3, S1, S2, S3. Test if the path T1, T2, T3, S1, S2, S3, as in the theorem satisfy that F together with the TIs together with the SIs is a pyramid. If yes, you stop and say G contains a pyramid. If yes, output G contains pyramid. If no, for all F, output G has no pyramid. Right? And the only kind of unclear part of this is why is this fair? Why, if for every frame the answer is no, you're not going to get a pyramid, you don't have a pyramid in your graph, and the theorem is, and the answer is that's exactly what the theorem says. If there was a pyramid, then when you hit on the correct frame, this simple algorithm would give you a pyramid. There are two things I wanted to say about that. Oh yeah, okay. So those of you who have been paying attention might notice that I promised you an algorithm that runs in time n to the 9. And in this algorithm, one of the steps is test for pyramids. And in the step where you test for pyramids, you run through all tentacles of vertices and you do something. And one might get suspicious. So the truth is there's a cleverer way to do it. What I described to you here is kind of conceptually the simplest thing to this is conceptually the simplest description of this algorithm. But really what you do is you don't include the S's in the frame, so that helps already. And then you pre-compute some paths ahead of time. You start by computing all possible paths between pairs of vertices in the graph or something like that. And then you just read your paths over the table. And there are kind of clever things you can do to bring down the complexity. And then the other group can do even cleverer things to bring the complexity down even further to 8.5. But this is kind of the idea. This is why it works. And I think maybe this is where I'll stop it. So what we just recap what I said. We're trying to test for odd holes, and we said there's 3 steps. And the first step was test for easy detectable configurations, which are C5, jewels, and pyramids. And then there will be a third step, which will now be easy to describe now that I told you what the shortest path detector is. And then the interesting part will be the second step, which connects it to. And I think that the first thing I'll do next time is show you kind of a rough idea of the proof of the theorem that was here, of the proof that tells you if there's any pyramid, then the frame for the shortest pyramid works. Because it's surprisingly simple. Once you understand that's what you need to prove, the proof is really not hard. It's just, when we did it, and as far as I know, nobody thought this way. Nobody thought you could test for induced subgraphs by just guessing a few vertices. As soon as it became plausible to us that you could do it, it wasn't hard to prove. So I'll show you, a little bit of that proof, and then I'll show you the rest of that. And thank you very much.
Yeah, thank you for the lecture.
And I'll also change those. This is a fillable pen. I'll change the filling. That's another thing I promised to do for next lecture.
Thank you.